ask again, please complete the online course evaluation. You should, everyone gets an email, how's that at work? Do they pester you about it until you fill it out? Yeah, good. So, please do, okay? All right. We will, all of the lecture notes and the last video of the class will be posted, so you'll have all that information. All right, so last time we had derived the famous Glauber correlation functions, which follow from the full quantum theory, thinking about joint probabilities or rates of photodetection associated with n photons at n photocounters. And the central object that appears is what Glauber defined here as the expected values of the quantum electric field operators in terms of the positive and negative frequency components. Okay, you remember the positive frequency components are the part associated with the annihilation operators, and the negative frequency components involve the creation of photons. Okay, so this is a kind of cross-correlation function. The objects that appear, if I ask about the rate of n photon joint detection, then these primes are equal to the non-primes, and we typically just write that in this way without the two arguments. And what that is equal to is the normally ordered product of the intensity operators. So whereas classically, if we're thinking about correlating the photocurrent associated with n photodetectors, we would just mix those n photocurrents together and look at the correlation between the photocurrents. In the quantum theory, what we have are these normally ordered products of the intensity operator. So again, what the normal ordering means is ignore commutation relations. Move all neg or creation operators to left, and the annihilation operators to the right. So this is a shorthand for this object where I just get rid of the primes. Okay? Is that clear? So for example, G2 of x2 and x1 is the normally ordered product of the intensity at spacetime point 2 and spacetime point 1, which is the normally ordered product of the intensity is E minus E plus at spacetime point 2 and the intensity at spacetime point 1. And how do I normally order this? I move all the minus negative components to the left and all the positive frequency minus. These don't generally commute, so I can't do that, but this symbol means do that. Okay? It's just a shorthand. So this is equal to define a normalized little gn as big Gn divided by the product of the G1 coefficients like that. Okay. So what does this represent? What does this denominator represent? The denominator, so this on the denominator is really the product of the average of the intensity operator at each of those space-time points. Right? Because that's what the G1 is. And so this represents, if, this object up top here is the correlation function between the two different intensities, which represents the joint probability, or something about, it's related in some way to the joint probability of detecting n different photons at n different space-time points. The denominator represents the case where those events are uncorrelated. Right? So if there was no correlation between the photons, or those events were completely statistically independent, then we would just say that that correlation function would factorize. So the denominator we sometimes call the accidental coincidence counts. Right? It's the coincidental coincidence counts. They just happen to be there at the same time. Those are the accidentals. So if this ratio is 1, then that means everything is just, all these events are completely uncorrelated. Okay? Now, we just by definition, as Glauber did, we define a field to be nth order coherent if Gn factorizes. Into some function of each of those variables. And if that's true, then the little g is 1. Okay. And we say it's nth order coherent. A coherent state, which is why he called it this, is coherent by this definition for all n to infinity. So in a coherent state, of course, as we briefly discussed last lecture, this kind of correlation function, if it's a coherent state, then each one of when this guy hits the state, it just this operator is replaced by an eigenvalue. And then the next operator is replaced by an eigenvalue, because the state is an eigenvector of E plus, because it's an eigenvector of the annihilation operator. It's a multimode coherent state. It will be an eigenvector of E plus. So in a coherent state, this thing would just be equal to the classical amplitude at each of those space-time points. where this script E is just the eigenvalue associated with that coherent state. Right? And so the correlation function factorizes no matter what n is. And that's what we define as a coherent state. And what we see is what that means also is that there's no correlation between those photon detections. And from the temporal point of view, if I thought about different events happening at the same position but at different times, then that is the condition for a Poisson distribution or Poisson process. So this is one and the same with saying that the photon number distribution is Poissonian and that there's a random photon events. Okay? So it's all self-consistent. All right. So now let's again remind ourselves about the Hanbury-Brown twist. Particular experiment of the related to a G2 type experiment, where we imagined we had some light coming in at a beam splitter, we split it off, we have two photodetectors symmetrically placed on both output ports, and then we take the photo current, we delay it, and we look at the product. Now, in the context of individual photons, we think about that as a coincidence counting experiment. Of the kind we introduced the whole photon notion thinking about the Granger-Aspect experiment of the 1980s, where they looked at heralded photons, photon coming, and they looked, then opened the gates and looked for correlations, right? Coincidence counting. Okay. Now, in the Hanbury-Brown twist experiment, what we thought about as photocurrents, as we said, we thought about this as just the correlation between the photocurrents, which are related to the intensity incident at some time and some later time tau. Okay, and that was what were measured in the original Hanbury-Brown and twist experiment. And if I looked at the difference between this and the product of the intensities, this represents the intensity covariance, or fluctuate the correlation in the fluctuations, right? Where if I think about, I mean, that's just a shorthand for the expected value of I minus the average I times the I at 0 minus the average I. This is what we would call the covariance. And when tau is equal to 0, this is just equal to the variance in the fluctuation. Right? So when tau is 0, the degree to which I see correlation between these two currents compared to what if I just looked at the product of the two currents on average independently, right? That's this guy. Then what I'm looking at time t equals 0 is the fluctuation in the intensity, right? And as I say, the difference between the average of the intensity squared compared to the square of the average. So now, how do we think about that picture in terms of the Glauber theory of photon counting? how do I think about that? So let's think about a single mode. Just to get going. The single mode could be in a cavity, or I could think about, so I might have, one mode here, and there's a creation annihilation operator associated with that particular mode. Or I might think about a temporal mode, where I'm thinking about a beam, and there's a particular time slice, and that time slice hits. Okay? And I'm looking, when I look at G2 at time t equals 0, what I'm looking at is so let's think about that. So G2, now if I thought about this for a temporal mode, I might say the following thing. Let's say if I look at this for a bunch of well, now I have n dot at T2 and n dot at T1. Right? That's the correlation in the photon counts where n dot at T is a dagger T. Right, as we discussed in the past. Right? So this is a shorthand for a dagger T2, a dagger T1, a T2, a T1. Is that clear? How the normal ordering works? Close your eyes, forget about commutation relations, move all your a daggers on the left, all the right, and just, it's nice. We don't have to worry about the fact they're operators. Okay? So this is a thing where I annihilate a photon at T1, and I annihilate a photon at T2, and I look at the overlap of that, like that. Okay. Now, if I think about, let's think about G2 at 0, where T1 equals T2, and I'm going to just set that equal to time equals 0. Then I'm going to call this a dagger, a dagger, a dagger, a, and forget about all the other labels. Okay. Really, I'm being a bit sloppy here because really this is a at 0, a at 0, a at 0, and then I have to really worry about the fact that these are rates. But I'm just going to look at this integrated over some time slice, so that I don't have. I'm thinking about this in a mode rather than as a rate. Because as this goes to 0, this would be a at 0. There would be a delta function commutation. Okay. All right. So this is related to the joint rate of detection of two photons in this mode. So this is, again, that. Now, I could look at this object. Now this is just some operator, and I could start doing manipulations with the true commutation relations. Once I've gotten rid of the normally ordering, it doesn't mean that everything commutes. This was just a shorthand. Let me write it maybe a slightly different way just to emphasize some facts, because this can be very confusing. So this is equal to this, which is equal to But this symbol means this. Is that clear?
Is that supposed to be an n dot?
That's what I just slurred my speech about. It really should be, but I'm going to say A is the integral of A of t dt and a little time slice like that. So this is in this mode. So I don't want to have to think. I want to think about it integrated over a finite instead of a set of measure 0. I'm going to look at it over a certain time interval. So otherwise I'd have delta functions that I don't want to carry around. Okay? That's what I mean by a single mode. All right? So it's a time slice that has a finite interval, which might be related to the time response of the detector. That would say the time over which the detector integrates before it gets a click. Okay? So, yes, you were paying close attention, and I kind of did this. Okay? All right. So, now this is some operator. I've gotten rid of this symbol, and now I can start manipulating it. So, for example, I can write this back in the terms of the number operator by commuting these guys. Okay? So this is equal to plus the commutator of that is -1, so that's equal to that. Is that clear? I just commuted A dagger with A. The commutator of A dagger with A is -1. Okay? So this is equal to n squared minus n. So the expected value of the normally ordered n squared is equal to the expectation of n squared minus the expectation of n. So now let's look at the difference between this and the accidentals. Okay? In the same way that I could consider what is the difference between the correlation in intensities compared to what it would be if they were not correlated. Right? And that was related to the correlation in the fluctuations of the classical intensity according to the semi-classical theory. But what is it here? So now let's consider G2 at 0 compared to the square of G1 at 0. That is to say, I'm going to look at the difference between the probability for joint detection or rate of joint detection minus the product of the rates if they were uncorrelated. Okay. So I'm just considering that object. In the same way that I considered the intensity fluctuations or the intensity correlations in the classical theory. Okay? So let's just look at what that object is. Well, that we just calculated that up here. So now I can put it together. This is equal to the mean n squared minus the mean n. That's what we just said up here. And then I'm going to subtract from that the uncorrelated piece, which is that. Okay. And so that, thus, is equal to the average of n squared minus the average of n squared minus the average of n. Or it's equal to the fluctuation in photon number associated with that state compared to the mean n. Okay? So that's equal to this. How What does that mean? Yeah, well, what if I put in a coherent state into that mode? What is that equal to? It's equal to 0. So, what this difference is, if I have a Poisson process, then the fluctuations in the number of photons will be equal to the mean number of photons. So the difference between the fluctuations and n, if it's greater than 0, we call it super Poissonian. Da, 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 super Poisson. Meaning more fluctuations than a Poisson distribution. And if it's less than 0, we call it sub-Poissonian. Okay. Right. If it's coherent, then it's Poisson, and this is equal to this because it factorizes. And that is equivalent to saying that the fluctuations is equal to that. So, if I come back to this board, if I shined a laser on this, I would find that the correlations between those photons is just equal to the product of the expected values on each side because they are uncorrelated Poissonian events. Okay? Now, let's think about this from the point of view of what we would say if we have classical light. Classical light is the set of quantum states which I think about as a statistical mixture of coherent states. That's how we're defining it at the moment. So if I have a statistical mixture of coherent states, then rho is, for the single mode, is a convex combination, as we like to call it, or a statistical mixture of coherent state density matrices, where P is a probability distribution. To be a probability distribution, it means that this function has to everywhere be non-negative. Otherwise, it's not a probability distribution. We also want it to be normalizable, and we could normalize it if we want, and we typically would, by saying that integral over the phase space, this probability is 1. Okay? For example, for a thermal state, this probability distribution is 1. It is so many probability distributions.
Gaussian.
This is over the amplitudes.
Gaussian.
It's Gaussian. Right? It's Boltzmann in the photon number. Cody, you had a question? No. Okay.
No.
Okay. Okay. Sorry.
I was going to ask about the probability.
Okay. Yeah. Okay. Well, there we go. So, as we said, for a thermal state, it's a Gaussian. But any classical probability distribution, honest-to-God probability distribution, is fine to find some particular, is a what we call classical light. Okay? Yes, sir.
Is the expectation value of I of tau independent of tau? Upstairs, if you wrote expectation value of I with no time argument, and then downstairs, you wrote it with
Yeah, if it's a stationary one,
So that we are assuming.
if it's stationary, this is true. Otherwise, I don't really need to do that. I could put, it's not required. The whole analysis is fine, whether it's stationary.
So
It's a more
it's not
general thing.
required.
It's not required, no. Okay, but for the moment, we're focusing on the single mode. So let us ask ourselves, what is this parameter in the context of the classical state? So let's look at the fluctuation in photon number under the assumption that our state is of this form where this is true. Okay. So let's calculate that. That is equal to the average of n squared minus the average of n squared, which is equal to the trace of n squared with that, minus There's a lot of different ways. I could have gone about this a slightly different way. Let me come back to a point in a moment, because I realize I could have made this a little quicker, because we're going to go in a little circle, and I want to come back to the beginning here. Okay, what is this equal to? Well, this is that, right? Which is alpha squared. We knew that. The mean number of photons in a coherent state is the square of the amplitude. And so this whole object over here is equal to the statistical average over the stochastic amplitudes of the intensity, right? And then I square it. What about this? Well, again, this is equal to A dagger A times A dagger A. And how am I going to calculate that? I have to commute through. So when you're taking expectation values with respect to coherent states, you want to put things into normal order by commuting them, because you know how the annihilation operators act to the right, and you know how the creation operators act to the left, right? So this is equal to, I mean, I'm going in a circle because we set it up there. I could have written it, used the relationship, but I have now A dagger A plus A dagger A. So this is equal to now I have alphas to the fourth plus this, which is the mean A. Okay, so that's this whole thing.
Is that not just alpha squared?
It is, but I'm going to leave it as that because I feel like it. So, putting this all together, what I see is the following. For classical light, the fluctuation in photon number is equal to average n plus the following. It's equal to the statistical average of alpha squared squared minus the statistical average of alpha squared squared. This is just another name for alpha to the fourth. So, what we see is for classical light, the fluctuation photon number is equal to the mean photon number plus the fluctuation, the variance in the intensity. Right? That's what this is. The difference between this, the difference between that and that is what I'm calling the fluctuation in the intensity. So, how do we think about this? Well, first of all, this is greater than or equal to 0 for classical light. As we mentioned last lecture, we can think about this as the particle contribution and the wave contribution. If I have a definite wave, so I have a definite coherent state, there's always fundamental fluctuation in photon number because of the corpuscular nature of the quantized field, and that fundamental fluctuation is Bosonian. But if I have, in addition to that, classical noise, which gives me just uncertainty in the statistical sense of what current distribution radiated that field, then I have additional intensity fluctuations. And that translates in the quantum theory to additional fluctuation in the number of photons I would expect in the mode. Right? So for example, for a thermal state, we had that the fluctuation in photon number was equal to the mean n plus n squared. That was the Bose-Einstein distribution. And we had that additional effect, which is what we have also thought about in terms of the Gaussian. The fluctuation in the intensity, as we saw, given that Gaussian distribution, we have exactly this additional factor here. Okay. Now, what that means is that classical light is super Poissonian. It has additional fluctuations beyond the Poisson noise. Okay? And so we have here our first litmus test for non-classical light. Non-classical light one feature it can have is it can be sub-Poissonian. There's no way to explain fluctuations in the photon number that are below Poissonian through the classical statistical theory. Said another way, in order for this to be true, this function has to be negative in some way. If that were true, then this could be a negative number. if I have a negative probability distribution. Of course, this is not a probability distribution. And this is our first example of something we're going to study, because I know we're all going to be there next semester, when we talk about quasi-probabilities. This particular way of expanding the density operator in terms of the coherent states is an example of writing things in terms of a quasi-probability distribution, which is known as the Glauber-Sudarshan P representation. We're going to talk lots about this next semester, about different kinds of representations. But the P representation is the first one we encounter. And the P representation, we can always write it down, but it's not always an honest-to-God probability distribution. If it's an honest-to-God probability distribution, then we call that classical light. If it's got negative regions or is highly singular, we call it non-classical. And such light cannot arise from just classical currents. We have to think about quantum emitters, because we had shown that if we had just classical currents, then we got classical light. Okay? So the first thing we see here is this business of Poisson versus sub-Poissonian. Seeing sub-Poissonian statistics is an indicator of non-classical light. It's not required for it. There are other features that we're going to talk about in a moment, but it's one we see. Now, I'm going to say a few more words about this. So another way of expressing this is in terms of the normalized. So if I look at G2 at 0, which for this, in this integrated thing, so I don't have to keep the dots around, was equal to this. This is equal to this.
Should that be at 0 now?
That should be squared. Thank you. Which I'll write as which is equal to the fluctuation in photon number so if I have coherent state G2 at 0, which is the ratio here of the coincidences compared to accidentals, is 1. For super Poissonian,
Super or sub?
either way, let's talk about super. Then this is greater than 1, and sub-Poissonian G2 at 0 is less than 1. This is sometimes, in some old-fashioned notation, I'm old, so I'll write it this way, as Q over N, average N minus 1. So the Mandel, the famous Lamb Mandel, another of the great heroes of quantum optics, the Mandel Q parameter, not to be confused with the Q function, which we'll talk about next semester, is defined as the ratio of the fluctuations relative to Poisson compared to N. And for non-classical light, Q is less than 0. And the minimum value is what? What's the minimum this can take on? Negative 1. And what is the state when that is true? It's a Fock state, right? So if I have no fluctuations at all, that's a Fock state, then this is minus 1. So it's a way of quantifying the degree, the Mandel Q parameter, little known these days, is a way of quantifying the degree of sub-Poissonian, okay? Just looking at it relative to the Poisson fluctuations themselves. So this is for a Fock state.
Question.
I'm listening.
Should that be Q over N plus 1 or minus 1?
It should be plus,
Okay.
indeed.
So then if we have a Fock state greater than 1, then we're going to have a G2 of greater than 0 still?
No, I mean, if I have exactly n photons, then at that point, G2 is 1. I'm sorry, is 0 in that case. I mean, this is always 1.
Because if we're in a Fock state and
Yep.
Q is minus 1, then Q over the average number of...
Right. Because there can be more coincidences in that case. That's correct, indeed. If I have something where the average N, I mean, the degree of negativity here, yeah.
I understand that.
Yeah.
Okay.
All right, good. Yeah.
Is this a proper measure of the quantumness of light?
I don't know, what does proper mean to you?
No, it's just that as we increase the number of at the number in a Fock state, it gets closer and closer to 0, right? Poissonian. So is that because it looks more and more like a Gaussian with a heavy mean, which looks more and more peaked?
I mean, if our Fock state gets closer to infinity, then our G2 is going to get closer to 1. It's going to look like a coherent source, right?
I mean, it's true that at this point, the degree of quantumness versus non-quantumness, one really needs to think about many higher order correlation functions. Really, this is only a useful measure of quantumness versus non-quantumness, as we're going to just look at in a moment. If I think about a feeble source, highly attenuated. Otherwise, I need to look at the higher order correlations. But if I have something that rarely has more than 2 photons in it, that's really when I want to be thinking about this. Otherwise, I really need to think about all the multi-order correlation functions.
So then if you would want to say, if you have a high photon Fock state, then you would just need a higher correlation function.
That's right,
determine
to
whether
fully
it's
characterize it. That's right, to fully characterize it. Absolutely.
On the same order of photon?
That's right. On the same order. That's the number of mean number of photons.
Okay.
So let's look in specific, let's look at that problem more carefully. Let's consider a case where the mean number of photons is very small. Okay, so let's have a highly attenuated source. Right. So now, let's take a look at this G2 at 0. Again. Now, let's look at this generally. Let me write the density matrix in the most general form. And I'm just going to write it in the Fock basis. Okay, so this is the matrix element. That's the most general density matrix. So now let me take this expectation value with this most general state. I'm not saying whether it's classical or not. I'm just saying that's just expanding it in the Fock basis. Now when I take this expectation value, only the diagonal elements contribute, right? Because this thing will annihilate 2 photons, and this thing will create 2 photons if it acts on the right. So it only when n equals n prime do any of these terms contribute. So this is equal to the sum over n, p sub n, and a dagger, a dagger, a. Okay. Where p sub n is rho and n. So now I can act this guy. When it acts on that, I get the square root of n, and then I get the square root of n plus 1.
Should be n minus 1.
Set, I'm sorry?
Should be n minus 1. Reacting on n. Lower the state, then again reacting on n should be n minus 1.
Yes. So this will be equal to the square root of n minus 1. Oh, you're saying, and then I act it again and I get a minus 1. Right. Okay. Very good. Okay. So now if the mean number of photons is much, much smaller than 1, then the first dominant, only the dominant contribution in this was the lowest case, is when n is 2, right? N is 1, this is 0, n is 0 at 0, n equals 2 is the first term. So this is approximately equal to 2 times the probability of there being 2 photons in that mode, when this is true. Now, how do I understand this factor of 2? Well, one way to think about this is sometimes called Bose enhancement. It came from the fact the commutation relations, if these were fermions, it would be a different story. Another way of thinking about it is in terms of these two photons, there are two different paths. So let's look at this in the case, though, if I think about this from the point of view of the two different kinds of states. If I have a coherent state, let's say a thermal state, what's the probability of having n photons in the mode for a thermal state? It's the Boltzmann distribution, right? Which, for bosons, is the Bose-Einstein distribution, which is equal to the mean n to the power n over the mean n plus 1 to the power n plus 1. We will learn all these things. And this is approximately equal to the mean n to the power n when this is true. So the probability of there being two photons in the mode is equal to the mean n to the power 2, which is equal to that. Because the probability of there being 1 is the mean n, right, for n small. So, when we have a thermal state, in this limit of small mean number, G2 at 0 minus the square of G1, that's the probability of finding two photons in the mode compared to independently finding them, is equal to twice P2 minus P1 squared, right? Because P2, right here, this is the probability of finding two photons, where we just, this expectation value, this is G2 at 0, which twice P2. But P2 was equal to P1 squared. So this is equal to P1 squared. So, another way of saying this Bose enhancement is that bosons like to be in the same mode. So the probability of finding two photons in the same mode is not just the product of one finding one photon and another photon statistically independent, which would say it was p squared. I have an enhancement here, right? This is equal to twice p1 squared. This is what we sometimes call photon bunching. There's more propensity to detect two photons in the mode for a thermal state than if they were statistically independent. What about for the coherent state? What is the probability of there being n photons in the mode? I'm listening.
Poisson distribution.
Yeah, it's a Poisson distribution. So it's the mean n to the power n over n factorial e to the minus average n. Right? That's the Poisson distribution. This is the Bose-Einstein distribution. And this is approximately equal to average n over n factorial in this case. Right? So, the probability of their finding two photons in, probability of finding one photon in the mode in this case is approximately equal to the average n. And the probability of there finding 2 photons in the mode is what?
U squared by 2.
Average n squared.
Average n squared, right? Because I said this is small, I can neglect that. So this is average n squared over 2. Factorial, which is 2. Ah! So, what is this difference here? What is G2 at 0 in this limit of feeble light?
Zero.
The difference is 0. G2 at 0 is equal to P2 itself, which is equal to n squared, or 2p2, which is n squared, which is twice p1. And that twice p1 is p1 squared. So, this was interestingly a big controversy in the 1960s. In the 1960s, lasers were invented. And Mandel said, oh, this is going to be, we're going to see an amazing enhancement of the Hanbury-Brown twist, because we're going to have this kind of Bose enhancement of many photons in the mode. And there we'll see this big enhancement. But it's actually the opposite. You see no change. It's not a correct statement. It's the thermal light that sees this enhancement of more photons in the mode. A coherent state, they're completely uncorrelated from one another. And so we see here in this case this difference between detecting 2 photons and independently detecting those photons. That difference is 0. Interesting. Yeah?
Why do we have to take a small intensity limit? Is it because these fluctuations get washed out at higher frequency?
That's right, for what we were just discussing. Yeah.
So then, if we're looking at this small average photon,
Yeah.
then how that G2 never mind.
So the point here is that I don't have a definite number of photons. My average number of photons is very small. So here's my photodetector. Nothing, nothing, click, 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 nothing, 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 click. So on average I see nothing. I mean, I see very small, but I see fluctuations. And this, I have these different distributions. For a thermal state, the probability that I'm going to see n clicks in that interval is this number. For the coherent state, this is the probability. There are different probability distributions. This guy shows that because of this Bose enhancement factor here, the rate at which I'm going to see this joint detection compared to the product of the rates of the single detection, right, is equal to this difference, twice P2 minus P1 squared. For the coherent state, that's 0. For the thermal state, there's an excess. All right, I want to conclude with the discussion now about this whole business of 2-photon interference. So I want to look now at G2, not at 0, but G2 for a tau bigger than. And so in particular, let's start with, to get to build some intuition about this, we must erase the board. Okay, that worked. Okay. All right, so, let's go back and think about our hamburger ground twist type experiment with 2 photon counters, photodetectors, and a coincidence count. Okay, and let's imagine that I have a 2 photon wave packet. Okay, so I'm going to say that the state that I send into this beam splitter, I'm going to, let's say I have a wave function psi and a wave function phi. So one of the photons is in the wave function psi, the other photon is the wave function phi. Of course, I don't know which photon is which because they're identical particles. We'll come back to that. Okay? So I'm going to create one photon in the state phi, and another photon I'm going to create in the state phi, acting on this. Where this mode is A, and this mode is B. Okay? And let's say that's my A in, and that's my A. Now I have to normalize this state, and to normalize it, I'm going to get 1 over the square root of 1 plus the inner product of those 2 guys. If psi is equal to phi, that'd be 1 over the square root of 2, right? Because that would be like A dagger squared. Okay, so now my coincidence rate is going to be something that is proportional to the expected value of the state with respect to the normally ordered So this is my G2 of tau. Okay. This is like the 2 intensities at the output port in mode A. 1 at time 0, 1 at time tau. So this is equal to right? That's my normally ordered product, right? I closed my eyes, I turned off the commutation relations, I moved all the A daggers on the left, and moved all the A's on the right. Okay. Yes, sir?
Are they both in A?
Because it's a good question. They're not both in A. One is in B. Absolutely. So let's do that. It's because I screwed it up in my notes. In my head, I got it wrong then. So these should be B.
Also, is that a sin or a psi?
That's in. And that's a B dagger. Thanks. So now I got to do this right because I did it wrong. Tell you where. Okay, so now I ask you, how do I relate the out operators to the in operators? Everyone did their homework, so everyone knows the answer.
The S matrix.
Do the matrix.
Right. So if this is a 50-50 beam splitter, then this is going to be equal to 1 over the square root of 2 A in with some phase, depending on how I have it, B in. Right? And B out is 1 over root 2 B in dagger minus I A in. That's just the scattering. Okay?
It should be plus I.
It's a dagger. Who cares? Everyone always focuses on the little details. I don't. You got it right. You're right. Okay. So, all right. So now what? Let's look at this object. Okay. This object over here, when I have the vacuum coming in here. I'm not going to put any photons into that mode. I'm going to put these 2 photons into that mode. So when this thing acts on this, it's only the A parts that matter, right? Because the B's will annihilate. Anything with a B will annihilate here. And the A's and B's commute. So this over here is equal to minus I over 2 A in at tau, A in at 0 over root 2 over here. There's a method for this particular madness. Acting on psi in.
Should one of those be a B?
No, they're all A's. They're the A's and B's out are related to A's and B's in, right? So the part that comes out here is a linear combination of this, and the part that goes here is another different linear combination. Anytime the B hits this guy, it annihilates because there's vacuum in the B modes. So I'm only keeping these terms. There'll be 4 terms when I multiply it out, but it's only this guy's that matter. Okay? And if I want to satisfy because I should make this plus, because it's really A, not A number. Okay, so now what? So this guy is going to be the conjugate of this. So this is equal to 1/2 the norm squared of this. That's why I didn't care about the minus sign. It went away anyway. All right, so now I ask you all, how the heck are you going to calculate this?
It would be nice if it were a coherent state.
It's not. But it's still kind of nice. What is the state? It's a good question. The state is this. Let's plug that in. I just plugged it in. Okay, now what?
Do your thing.
That's very good. What thing? I love it. That's a good answer. How am I going to evaluate this? I'm listening.
I can write that state like some integral of time here.
We could, yeah. So I can think about these guys. So let me ask you a different question. Maybe let's simplify. There's so much decoration on here. There's an in, there's an out, there's a bracket, there's a sign. Let me ask you a different question. Suppose I wanted to calculate this. How would I do it?
Commutation.
I use commutation relations, right? Well, let's do it the other way. That's
Zero,
zero. That
that's
was a cheat. Trick answer. I could use the commutation relations. What you always want to do when you got the vacuum is move all the A's through, because then you know what the answer is, 0. So this is equal to that, right? Because if I put them in the other order, I get 0, because we just said that. So now all I got to do is calculate these commutators. All I got to do. I'm going to do my thing. And keep you late because, you know, we're almost done and there's just so much got to finish. So I have A at tau, A at 0. Everything is in now, so I'm going to forget about my ins and outs. I got my A dagger psi and my A dagger phi. And I got to calculate that commutator. And so now I use the rules. That's all ultimately going to act on the vacuum, so I'm just going to put the vacuum there. So that equals that, because I put it the other side would give me 0, right? Which equals we agree so far? So what I did is, using the rules of how you move through this, I would take this out, commute it, that on the other side, this annihilates it, so that's one term, right? And now I do this, and I bring this guy out to the left, or the other guy out to the right. Okay? Let's get a different color. That might have a little. So now this, I remind you as this, with a little bit of work, as we discussed at some point or other, is equal to that. So this is equal to the wave function psi of 0. and this is equal to the wave function phi at 0.
When did we do that? How long ago was that?
When did we do that?
Yeah, I don't know.
Some lectures ago. It comes back to what Shiva was reminding us, that this is a dagger, is the integral over time, a dagger of t, psi of t. I can make that a dummy variable, and then this follows.
Okay.
And then the commutator at different times gives you a delta function.
I'm sorry?
And then the commutator of
And then the commutator is a delta of t.
and then you can compute the integral.
Yeah.
Okay.
All right. So this now is equal to phi of 0, a of tau, a dagger of psi, plus phi of 0, a dagger. Acting on the vacuum. And now what? How am I going to evaluate that?
Again, you
I use the commutator again.
Use the
I can
commutator.
replace this by its commutator.
You get psi of tau and phi of tau.
Exactly. And that becomes psi of tau. And this becomes phi of tau. Oh, this is so beautiful. I love this so much. So now, this whole thing is equal to a half phi at 0 psi at tau plus psi at 0 phi of tau over root 2 squared. Oh, that is so good. What did we just find? This joint coincidence rate is related the square of the two-photon wave function. But the two-photon wave function is symmetrized because these are bosons. I can't say that one of the photons was in the packet psi and the other one was in the packet phi. I don't know which one hit. So let us now express all of this out. This is now equal to 1/4
Should there be another star on this star?
Yeah, this guy should be star. Thank you. How do you interpret that?
Even if there is already entanglement between your photons, they need to be like in the same time for your correlation slope here.
Well, I didn't have an entangled state to start. I just had these two states. Really, the question I'm asking is, what are these different processes? So there are different processes that can occur. What are they that correspond to coincidence counting?
They both arrive at one detector or the other detector, or they split?
So there is, there are these two wave packets, this is the sine wave packet. This is the phi wave packet. Maybe they're not the same shape. Or this guy goes over here, and this guy goes over here. Now, this is the case where, this guy goes over here, hits at time 0. This guy gets time dilated by amount tau, and I look at the overlap of these two guys. That's this. Or this guy goes to this detector, gets delayed by an amount tau, and then I have a coincidence. That's this. But what's this?
Interference.
That's interference. This is two-photon interference. Okay. So, what we see is in this coincidence counting, we can see interference between more than one photon and itself. There's interference of these different processes, different histories that can lead to the same final outcome. In quantum mechanics, say, we have to add the amplitudes for them and then square. Now, if these two wave packets never overlapped with one another at different taus, then this coincidence would be 0. So we can see, even if we had this idea beyond, if we had a thermal state with a statistical mixture of different photons, we're just looking at the two-photon component of it. And the question of whether we see coincidence counts in the Hanbury-Brown twist is just to ask whether the wave packets of these two photons overlap with one another. If they don't, then I see the statistical product here. This goes to 0. So we can understand the Hanbury-Brown twist effect in terms of two-photon interference. In the same way that we understand the double-slit experiment or the Mach-Zehnder experiment in terms of individual quanta interfering with different histories. However, we also know that we can explain the photon counting we see in a double-slit experiment or in a Mach-Zehnder interferometer in the semi-classical theory. We don't need no stinking photons. We just need classical light and Poisson fluctuations, or classical light and super Poissonian fluctuations. So just because it can be explained by photon interference doesn't mean it's required. It's not the smoking gun of non-classicality. We saw one smoking gun of non-classicality, the sub-Poissonian statistics, and I want to conclude now with the last smoking gun that we're going to discuss for this year. And that is the question, let's look at this correlation function now, not for non-classical light of two photons. Let's say we have classical light. Let's look at this object again for classical light. So I want to look at my G2 of tau, which is equal to my, I'm going to look at a single mode here. Let's look at the following thing. Now I'm going to look at this object, the one that I defined before. Let's consider this guy for a particular mode. I'm going to have classical light, which I'm going to look at as a probability distribution over my coherent states. Which now are multi-mode. So this object is equal to the statistical average over all those functions over the probability distribution so classically, I just multiplied the intensity of the two output ports. Now I'm just statistically averaging that. All right. Now, this object looks like, from the point of view of functional analysis, as the inner product between two functions. Right? If I look at the integral of two functions with respect to one another, this is like the inner product of two functions. If this is a positive probability distribution, I can think about this as the inner product of this function with respect to that function. This is a well-defined, the same way that we think about inner products between wave functions. Now by the Cauchy, oh no, so I swear, and these are squares. By the triangle inequality, or the Cauchy-Schwarz inequality, we know that A dot B is less than or equal to the magnitude of A times the magnitude of B, right? And the magnitude is the square root of the inner product of the thing with itself. So G2, this is less than or equal to the square root of the inner product of the function with itself. Times the inner product of that function with itself. That's the triangle inequality. But if I have stationary statistics, then the inner product of this with itself is equal to the inner product of that with itself, because it only depends on the time difference, which is equal to G2 at 0. And so we conclude with the following conclusion. For this classical light with stationary statistics, G2 at tau is less than or equal to G2 at 0. Or said another way, G2 at 0 is always bigger than or equal to G2 at tau. This is what we call photon bunching. So if I have classical light, what it says is that the probability that I'm going to see two photons at the same time is always bigger than the rate at which I see them separated in time. So if I looked at G2, as a function of tau, it always looks like this. G2 at 0 is always bigger than G2. So this is if I see the opposite, it cannot be described by classical light. If the photons are anti-bunched, means that they're more likely to be separated from one another than together. Yes, sir.
Is there a term for when G2 is equal to 1?
Coherent.
There's bunching, anti-bunching, and then coherent?
That's right. It's bunched or anti-bunched, but otherwise it's coherent. So if I look at this again relative to G1 squared, then this is 1. This is 2 for thermal light. And if I have something like this, that shows both sub-Poissonian and anti-bunching. Now, last point I want to make. I don't have to have both. Suppose I had something that looked like this. What would you say about that kind of G2 function? Is it classical or non-classical?
Classical.
It's non-classical. It's non-classical because it's anti-bunched. But it's not sub-Poissonian. In fact, the first experiments that demonstrated photon anti-bunching were done by Jeff Kimball when he was a PhD student of Lynn Mandel. And they saw anti-bunching. But they didn't see sub-Poissonian statistics. It's very, very, very hard, it was in the 1970s, to see sub-Poissonian statistics because you needed to have single atoms. And they didn't have single atoms, they had a beam of atoms, which had, so they had extra noise. They couldn't see the light emitted from one atom. Once you see the light emitted from one atom, that sure ain't classical light. If you have a beam, a thermal beam of atoms, you're going to have some fluctuation, but they did see anti-bunching.
When was this?
1977.
When was Henry Brown's 50s?
The 50s. The 50s.
When did they translate the radio interferometry to quantum optics?
The 60s. I mean, so, you know, the Henry-Brown twist was done with thermal light because there weren't no lasers in 1958. And the whole question of distinguishing classical versus non-classical was done by Roy Glauber in the early 1960s. And then when the laser came around, it was like, oh, we're going to see a big Henry-Brown twist. And Glauber said, no, that's not how it works. You're going to see coherence. But a point here is that we don't have to have all of the features. For this kind of correlation function is not consistent with classical light because it shows anti-bunching. But it is not sub-Poissonian. You don't have to have all of those features. I can have light that is super Poissonian yet is anti-bunched. All right. I want to just say now what we have learned here now, and where we're headed into the next year in our next semester is, what we've studied this semester is this question of coherence. And in studying that, we were thinking about optical coherence. And in thinking about optical coherence, we've now started to think about not just the properties of individual quantum systems, but the correlations between those quantum systems. What distinguishes classical light from non-classical light is not the properties of the individual photons, but the correlations between the photons. And that's where we're headed. What we've mostly studied this semester is what is sometimes called quantum 1.0, meaning the quantum coherence associated with individual quantum systems, be they individual atoms or individual photons. What we now like to call quantum 2.0 is the quantum properties that are associated with the entanglement or the correlation between particles. And that's what we're going to study into the next semester, is thinking about how, more generally, to distinguish what we mean by quantum versus classical. And the way in which we now quantify those differences, not just in terms of physics definitions, oh, it's a classical current, it's a non-classical current, but in terms of the resources that those states have for information processing and what non-classical light can get for us. Okay? So, for that, I will conclude. Everyone have a wonderful holiday. I look forward to your final projects and look forward to seeing everybody in class next semester.